Swayam Prabha. Digital India. Educated India.
Welcome back to the lecture series on Foundations of Cyber Physical Systems. So, if you remember in the previous lecture, we discussed about the arbitration scheme that we have in Canvas. So, with that we will now move to some other properties here. For example, what are the different error handling schemes that you have in Canvas? So, there are several checks. For example, these are things we have already described while we define the CAN packets, and now we will just point out the different checks that were there. For example, you have this CRC check. So each receiver will accept the message, and by looking at the message payload, it will recalculate the CRC using the known polynomial between both the sender and the receiver, and it will compare the value. And if you see that the CRC that is computed is different, then it knows that the original value changed from x to some x prime, and it will accordingly now send an error flag. Now, whenever the receiver will detect an invalid bit in the CRC delimiter, then also it will send an error flag. And similarly, if it finds such a thing happening in any such well-defined space like the ACK delimiter or the end of file. So, if you remember, the CRC, the ACK delimiter and the end of file, they have well-defined things that they are going to be of 1 bit or 5 bits, and they will be recessive. So if there is any violation of those things, it will be sent as an error flag, right? Similarly, there is a 3-bit inter-frame space. So if that is not maintained, that is also an error. And finally, you also have the ACK check. That means each receiving node will write a dominant bit into the ACK slot. So that means whenever the transmitter sends the acknowledgement in the slot, the receiver will set it to be dominant, right? So that is a switch in signal value that the transmitter can see, and if it cannot see that, it will go to a retransmission, right? So that then also an acknowledgement error will be flagged. There are also some bit level checks. That means so these are the previous things are at the packet payload level. Now at the bit level, if you remember the property of CAN, that whenever a bit is being transmitted, it is simultaneously also read by the receiver. So if we can see that, well, whatever I am transmitting, the bus is not having that value, then that's a bit level error that will be immediately detected. And also you have this bit stuffing, which will mean that whenever there are 6 consecutive bits of the same level, that is not allowed, right, due to the bit stuffing rule, which is supposed to change the polarity there. So if that is not maintained, then a stuffing error at the bit level will also be flagged. So all these things are there, and they should be able to prevent the CAN data getting corrupt due to some random noise or due to some random attack happening on the system through this kind of error handling scenarios. Now, what happens if there are errors? So these are designed to be very robust systems, right? So that means if there are 1 or 2 errors, the system is supposed to tolerate them, right? And in each CAN node, there is a transmission error count and there is a reception error count, the TEC and the REC count that is maintained. So on detecting the error, this node, whether the transmitting node or the receiving node, they will immediately abort that particular transmission and they will broadcast an error frame, and the respective nodes, the transmit node and the receiving node, will increment respectively the transmit error flag and the receive error flag, the error counts by different values. Now the transmit error count increases by step of 8 and the receiving error count will increase by a step of 1 as per the protocol. Now after this, if there is an error-free message transmission as well as reception, then these TEC and REC values both will decrement by 1. Now so these are the rules based on which the transmission and the reception error values increase or decrease, and based on those values the system can be in 3 possible states in the error mode. it can either be in an error active state, it can be an error passive state. So error active state means it is pretty much normal and the transmission and reception errors are below 127. If any of them is greater than 127, then they go to error passive mode, where they are highlighting that they will send an error frame, but at the same time they also have the ability to transmit other messages. Although they are sending an error frame, which is kind of a signal that, well, I am of late getting lot of errors. Okay. However, if this transmission error count of some particular node goes beyond 255, then it is temporarily taken off the CAN network and it goes to what we call as a bus off mode. So just repeating the previous states in an elaborate way, an error active mode will transmit and the active error flags. So basically there is, like we said, that in this mode I am doing my normal transmissions, but if there are some errors happening, then I will transmit this error flags, which is basically 6 dominant bits and the error flag delimiter, which is 8 recessive bits. So that's a set pattern, and this pattern represents the error flag. Whenever it detects the following kinds of errors, like violating of bit stuffing rule, and then all other nodes are suspended and it will just 1 minute. So it will just see that whether these bit patterns are not following that standard bit stuffing rule of CAN, and in that case all other nodes will respond by transmitting the error flags too. So that is the error active mode. And in the error passive mode, they will transmit the passive error flag. As you can see that whether I am in the active mode or in the passive mode, it's kind of represented by what kind of error flag I am sending. In the error active mode, I am sending 6 dominant and 6 and 8 recessive bits, and in case of the error passive mode, I am sending 6 recessive bits instead of the 8 recessive bits, right? So in this case, the other nodes will not hear this node complaining about the bus error. So if I am in the active mode, then the other nodes respond back by transmitting error flags. If I am in the passive mode, then the other nodes will not hear me complaining about the bus errors. That's the difference, but still in both these nodes, more specifically in the active node, fine, I mean, we are able to do our normal transmissions also, but whenever we are facing this particular kind of errors, we are transmitting the error messages, error flags, and depending on whether this error flag is acknowledged by the other nodes, that is kind of the distinguishing factor, that whether I am in the error active mode or I am in the error passive mode, right? Now, as I am repeatedly saying that even when I am in these modes, they just tell me that they just kind of make a distinction in terms of what is my history of error counts. Is it too high or it's moderate, right? But in both these nodes, I am still able to do my other works. That means I can transmit other messages also. But once it goes to this thing that is TEC is beyond 255, then I am in the bus off mode. Then I am not allowed to transmit anything on the bus at all. That is the bus off mode where I am temporarily taken out of the network. I mean, that means I am kind of ignored by all the other CAN nodes in the system. So in general, when so we will get back to this discussion in future when we talk about security of automotives, specifically CAN bus security. We will see that how this mode has got associated vulnerabilities and they can be exploited by some attacker ECU to kind of intentionally make a victim ECU go to the bus off mode, and then the attacker ECU can actually assume the identity of the victim ECU. So that is a possible attack that happens, and we will see how that happens. So now coming here, we can talk about what is a valid CAN frame. So it's a frame where the message is considered to be error free when the last bit of the ending end of field is received in the error free recessive state. So the EOF is again going to have a well defined bit pattern, which is the recessive state. if I have not got any kind of error in the previous bits, and if the EOF is also received in the correct pattern, then I will consider it to be a valid can frame, right? Now, if I see that well EOF is dominant, then I will think that there is an error and I will ask the transmission to be repeated, okay? And in general, such corrupt messages are automatically retransmitted as soon as the bus is idle. That means in the next transmission cycle. So, just coming to a small discussion on how CAN messages are scheduled. From the arbitration thing, we have understood something that in general, for such CAN messages, when you have to send multiple messages, you have to schedule them inside a bus. There is a difference between scheduling of packets in a network and scheduling of processes or tasks in general in an embedded system or a computer. Because we have schedulers in normal embedded processors or standard desktop processors which are preemptive. That means a high priority message, a high priority task can preempt a low priority task. Things like that happen, right? So that is the standard in thread scheduling. But unlike that, when we have network messages in the CAN bus, it's non-preemptive. That means that means while a low priority sender is sending his message, even if there is a high priority message, he cannot start sending the high priority message and make the low priority one preempt the bus. So no such thing happens in the CAN bus. So there is an arbitration. Whoever wins the arbitration, he will transmit, and while he is transmitting, if another low priority message comes, that guy has to wait. So it's non-preemptive in that sense. But the thing is, as we have seen that the data lengths are too small, it's up to 8 bytes. So the overall packet size is also small. So this will keep, one may think that well, if there is no preemption, then sometimes some specific message has to wait for a lot of time. There can be a lot of delay. But in this case, no, and these delays can be easily bounded, and the short message length will keep these delays to be quite small. So that is the advantage of having such scheduling. Now coming to the other issue, that what about the worst case transmission time for CAN bus? So if I have an 8-byte data frame with 11-bit identifier, so typically we can see that we can reach up to a speed of 1 Mbps in the worst case. So now let's get into an idea like how CAN bus loads are computed in general. That let's say I have a set of CAN packets to send, we give their periodicities, then how do I know that what is the total CAN bus load? So this is a very simple computation. So the bus utilization is nothing but the total number of bits that have been consumed divided by the total number of bits that are available. So you have a bandwidth of the bus which will allow these many bits to send, and you actually send some number of bits, so just that fraction, right? So how do you calculate it? To calculate it, first of all, you have to choose a time window. Now that amount of time you will choose is typically something greater than the slowest periodic message on the network. So you will have multiple messages with different periodicities. So let's say the slowest message has a period of 100 milliseconds. So if you take a window of something more than 100 milliseconds, that means in this window you will have at least one instance of all the messages. So you have a time window inside which you can see all the different kinds of bus loads, and you can choose something greater than this. The reasonable choice would be to choose a hyper period. That means the LCM of all the periods. So that would be a choice of period inside which you will have all the messages repeating integer number of times, and this is the pattern that will keep on happening on the system. So you can actually do that. So you will like to identify what all are the periodic messages, and for each of these messages you can approximate the total bit size of the message by adding 47 bits to the data field. So let's understand why this 47 choice is coming. So if you see here, apart from the data field which is a variable 0 to 8, all other fields are of fixed length, right? And they would sum up to 47. So if you just sum up the number of bits of all those other fields, you will get an interference space. Up to interference space, you will get this number of bits as 47. So get your data size plus 47. That's your packet size, right? So that is the total number of message bits. Now you multiply that by the number of transmissions that are happening inside a time unit, and so that would be the number of message bits that are consumed. and you just sum it up for the total over the all the messages, right? So that would give you that, well, inside the time window that you took, what is the total number of bits that have been transmitted, and for what you budget for worst case. That means in the worst case there can be some more transmission, so you can have a suitable multiplication factor, let's say 10% more. Okay, now that would give you a value which of the worst case estimate of total bits consumed divided by total bits available, and that is your percentage bandwidth. So let's take a sample example. Suppose in a CAN system you have nodes which are sending messages like this. So you have messages with periodicity 100, 500 and 100 and 500 millisecond and 1 second, and the data bits are like data size is like the payload is 2 bytes, 4 bytes and 8 bytes. So well, it's an easy calculation then. So if I just take this example, so if we just work it out, so that it's given in number of bytes, right? So you just have to take this plus 47, similarly you take this plus 47, so the periods are all given, right? Now let's say we have this transmission window, we have a transmission window that is 1 second, right? And 1 second is also an interval inside which I have a integral number of all these message instances occurring here, right? So if we choose that, then inside that how many these message instances I can see. So I will see 10 instances of this, and I will see 2 instances of this, and I will see 1 instance of this, right? So overall you will have 10 times 63, so over this 1 second window the number of bits that you are consuming is this 899, and you can consider that worst case factor of 10%, right? So this would roughly go to something right 989, right? Now let's say you are given this baud rate of 125 kilobits per second, right? So essentially what do you have is something like so it's pretty low. It is a very small percentage. You can have so many more messages here with higher priorities and other things. Even if you have something less, you can have a 1.25 kbps, then this will become something like 79%, right? So that's a very simple example here. So that's overall a summary of CAN. And just to think of what can be the drawbacks. So the drawback is for example, you have this kind of error frames, overload frames and retransmission. So if it's a non-ideal scenario where these things keep on happening, then the message latency becomes non-deterministic. As long as these things do not happen, everything is well defined, right? And also with amount of traffic increasing, I mean CAN is designed to be a low data rate thing, right? So then the message latencies will increase because you will be arbitrated out multiple times, and all these things will keep on happening, right? So one question that may come is, how do the ECUs, multiple ECUs can be connected on the CAN bus, and how the periodicities can then be defined? Well, we have understood one thing, that if I mean there is this arbitration happens, that means you should, if you have a low priority message, you should not try to send it at the times when the high priority messages are being sent, right? Now, it depends on how these messages are generated. If these messages are getting generated by some periodic sensor, let's say, or some periodic controller, if it's a control message, right, then well, you will like to send them with the same periodicity. So one option is to create a static schedule of such messages where you do not have this issue, or but that's also not possible, right? Because then it becomes a fully kind of deterministic system. I mean, in CAN, the reason you have arbitration is, well, things may also be event driven. That means some messages will be generated following some events, which I don't know when they will happen. But the fact that that message will be transmitted at that time or not is dependent on the existence of another higher priority message at the same time, right? So depending on this issue, well, I can have a statically scheduled set of messages. Then basically the arbitration is never coming into play. At every unique point, I will have one message to send from some node. Or like I said, that if messages are generated in an event-driven way in other ECUs, then it's not possible to have them statically scheduled. They will be coming dynamically, and whether they can go or not will be depending on the arbitration and existence of other high priority messages, and that will lead to the latency getting increased. And it may so happen that some event based message that is generated is delayed quite a bit. I mean, it may miss its deadline also. So all those factors need to be looked into when somebody is designing a CAN system. That, well, suppose right now this CAN system has these messages, and I am attaching another event driven system into that, whether it happens that whenever this event driven system is generating some message in specific cases, those messages are getting overly delayed due to the existence of such other messages or not. So that becomes a question. One option is to have time triggered CAN, TT-CAN. So this retains the original CAN's data link layer protocol, but it also provides a time triggering and a periodic communication which is clocked by a time master's reference. So there is a time trigger based on which the communication happens. We are not going to the details of this. This is used in certain cases. So as you can see, we said that CAN is pretty much event driven. Here we have event triggered messages in CAN, but here we may have time triggered messages also, right? That means the period between any two such reference consecutive messages here is a basic cycle, and this time window of a basic cycle can be used for periodic messages and for spontaneous state and event messages. That means you have specific time windows which can be used exclusively for periodic messages, and so those windows are exclusive for periodic messages, and there are windows where we can have them for spontaneous event driven messages. That means we have two different ways, right? We can say time triggered periodic messages, or we can send event triggered messages among which there would be some arbitration that is required. So I think for us is just what we are trying to say is that, well, unlike CAN, which is kind of purely event triggered, right? I mean, messages coming in arbitration, it may be possible to also have time triggered messages. So what does this mean? That when we have that exclusive window, right, that means this is the slot when only periodic messages will go, it doesn't compete for bus access. That means whenever there is, it's like static scheduling of messages. Whereas for the arbitrating window, when I have the event triggered messages, they will be competing for bus access. Okay, so that's like bringing in two different philosophies of time triggering and event triggering together. So just to summarize, in simple CAN, we don't have this kind of a distinction. What we have is, well, messages can be sent, messages can be generated, right, based on some events, and while the messages are sent, it has to be arbitrated. But like I said, that may also be an issue because due to arbitration, latencies become non-deterministic. Because right now I want to send a periodic message, whether I can send that message once every each time period, I really don't know, because it depends on the existence of other high priority messages. So it's always under arbitration. Rather than that, if it is the case that there are time windows, some of which are exclusive, that means some of the bus cycles are reserved for periodic messages and some of the bus transmission cycles are reserved for the standard arbitration based scheme that we just discussed. So that's a mixture, right? So that's something that TTCAN tries to do, and this basic transmission cycle is defined by this idea of basic cycle here, which is kind of the difference between two consecutive special messages called the reference message. And this reference message is basically something which is time instances which are generated by some periodic clock. Okay. And it has got other properties like it doesn't rebroadcast the corrupted messages or invoke error frames, something that the CAN do. In TTCAN those things are not there. Now there is another competitive protocol to TTCAN which has the those ideas also, like whether you can have I mean whenever you are having a communication frame, it can have two parts. One is the static part where you have fixed periodically triggered messages like the ones we want, and you also have the dynamic part where the messages will be sent based on arbitration. Okay, so these are named as the static and dynamic segments in a flex-ray transmission cycle, and the static segment is made of identical length time slots which you can assign to different nodes, and each node transmits this message synchronously in its reserved slot. So you can understand that in a flex-ray cycle, this is a full transmission cycle. This is your static segment. Now this static segment will be statically divided among these nodes. Okay, so that means each of these segments are having specific slots which can be reserved by individual nodes, right? And in those nodes, those slots reserved for the respective nodes, they can send their messages. So there is no arbitration happening, right? Now the dynamic segment has something like a polling mechanism. So that means if I want periodic messages to be sent without latency, I must put them in the static segment. But like we said that we will also soon see that later on when we are doing schedulability analysis that making things completely static is also a wastage of resources. That is why people like to keep things dynamic also, or event driven also. Okay, so in the dynamic segment we need some kind of mechanism to decide who will send and who will not send, right? So in case of flex ray, each of the nodes are given the opportunity to put an event triggered or asynchronous message on the bus in a priority order using something called a mini slotting timing mechanism. We are not going into the details here because we are just telling you what flex ray is. We are not going into the details of flex ray here as part of this lecture. Here we are just covering the details of CAN. The only point we are trying to make here is flex ray allows you, just like the idea of TTCAN, it allows you to have slots for static messages with fixed slots, and some part where you have some arbitration or some polling where there are messages which are generated at non-fixed times based on some events, right? They are not time triggered, they are generated due to some events. I don't know when they will come, and when they are generated they have to compete through some mechanism. Okay, so that's this other kind of protocol called flex ray, and that also has got some use in automotive systems. Now, the CAN is actually used in many standard microcontrollers. I mean the CAN interfaces are provided. That means these microcontrollers understand the physics of the CAN protocol, the different protocol rules and all that. Similarly, there are microcontrollers which understand the flex ray protocol also, and there are those transceivers are often attached to such microcontrollers. So in a summary, CAN is ideally suited for applications where you have a large number of short messages. Message lengths are small because of this limited data packet length, and you don't want them to suffer due to latency, because and as long as the message lengths are small, the latency is the delays are not much, right? So for them CAN is suitable, and CAN is highly reliable because if there are errors I can catch them, and the well-defined arbitration scheme tells you exactly when your message will go or whether it will not go. These things are quite well known. Nothing is probabilistic here. So it is suited for data, cases where the data is needed by more than one location, because you see CAN is more like a multicast thing, so the message can be read by anyone. So as long as the message is transmitted, and for situations where multiple nodes are requiring the message, CAN is basically quite resource friendly. It is nice to use CAN in those cases, right? And for faulty nodes, they get automatically dropped from the bus because of that error based protocol. We saw that the nodes have a count of how much error they have faced, and in case the number of counts are high, they will first transmit error flags. Then they will go from an active to a passive mode, where the error flag will change, and finally they will go to a bus off mode, where they will wait till their transmission counts go further down. But there is also another cheap network, the lean bus, which is also used for some specific kind of control loops in automotives, but none of these are going to be used for high bandwidth applications, and there are a lot of high bandwidth applications nowadays in your system, right? For example, self-driving vehicles or vehicles with connected mobility features, they use a lot of camera sensors, radar and LiDAR sensors, and those sensors stream in lot of high bandwidth data, right? Lot of high resolution data frames with a high bit rate. That is something that cannot actually support, and they may be supported by things like automotive Ethernet. And also for the infotainment part, the media part, there are other protocols like MOST. So from a design point of view, this is used typically for low bandwidth but reliable communication when that is a requirement. For example, real-time control of engine or other car systems like the electronic stability program, which is the vehicle dynamics controller and other packages. So that's the primary usage of CAN. With this, I will end this lecture here. Thank you for your attention.